everybody. This lecture is on oscillatory shear testing of viscoelastic material. So, this oscillatory shear testing is commonly used for a viscoelastic material if you want to characterize the material response over a wide range of time, or we call it as a frequency, which is the inverse of time. So, in this study we are going to restrict the response of a material to a very small deformations. That is why we call it as a small amplitude oscillatory shear for a bitumen. So, under very small deformation we assume that the response of the material is linear. So, all these material functions which we are going to define it for the oscillatory shear testing is applicable when the response of the material is in the linear regime. So, this is going to be the outline of our presentations. First we will see what is oscillatory shear, and when we subject the material to an oscillatory shear, what are the material functions that we need to define for a viscoelastic material, followed by we will calculate what is the energy dissipation for an oscillatory shear testing. We will also see a few constitutive model that can be applied for predicting the response of a viscoelastic material under oscillatory shearing. And finally, we will discuss few experimental investigations that we conducted, especially for a bitumen, and followed by we will summarize what we discussed. Okay. So, oscillatory shearing, as we said, is nothing but a shear flow, inducing a shear flow in a material. So, in an oscillatory shear, we keep a material between two plates, maybe a parallel plate as shown in this figure here, or between a plate and a cone system, and we keep the bottom plate fixed and the top plate oscillate, or in case both plate oscillating in a different directions. So, by doing this we are subjecting the material kept between a two plate to a shear flow. So, in a generally for testing a bitumen we use a parallel plate geometry in which the diameter of the parallel plate can be varied, or generally we use 25 mm dia or 8 mm diameter. 8 mm diameter or a small diameter is preferred when we test it at low temperature or when the material is stiff, and under high temperature we use a 25 mm diameter. This high temperature, low temperature, we have to be careful in defining the limit for a high temperature and a low temperature. So, now if this is high temperature, is like the material should not flow when you keep between the two plates. So, we cannot use this parallel plate geometry when the material is Newtonian. Likewise, you cannot use this parallel plate geometry when the material is very stiff at a low temperature. General temperature range for a bitumen to use this parallel plate geometry is maybe in the range of 10 degrees Celsius to, or maybe as low as 0 degrees Celsius to maybe 70 degree or 80 degrees Celsius range, 70. So, low temperature range will be in general, again it varies depending on the binder stiffness, and high temperature range will be like 70 to 80 degree, again it varies with the binder stiffness at this temperature. So, and depending on the geometry we also vary the height of a sample. We keep 1 mm height for a 25 mm dia, and we keep 2 mm height for 8 mm diameter. So, it is oscillatory shear is nothing but subjecting a sample to a shear flow. So, we keep a sample between a two plate, we oscillate both the plate or only a top plate in a specific pattern. In a cone and plate geometry, you see the top system is a conical structure. So, and since it is a conical assembly, the gap here is limited. So, it will be in the order of microns, maybe 0.0475 mm. So, in the order of microns. So, this gap being very small, we cannot use for testing a material that has a particle size of a larger distributions. For example, if you want to select a geometry based on the particle size, we at least keep a height of a sample to be minimum of 3 times the size of a particle. D here is the size of a particle size, maybe a maximum size, and h is the thickness of a sample or gap between 2 plates. So, we keep a height to be minimum of 3 times the size of a particle. So, mostly if we test a modified binder, we use a parallel plate system. So, in an oscillatory shear system, we keep a sample between 2 plate and oscillate. So, while doing this, the particle between a 2 plate is not subjected to a uniform motion. So, if a bottom plate is stationary and the top plate is rotating, so the motion of a particle sticking to the bottom plate will be 0, or the velocity here will be 0. Velocity will be 0 at the bottom plate. So, if the top plate is oscillating, so when the velocity will vary from 0 to maximum, when the height varies from 0 to maximum from bottom to top. Likewise, the velocity of a particle at the center will be 0 and the velocity of the particle at the periphery will be maximum. So, when you move along the radius, the velocity of a particle will vary from 0 to maximum. So, this is in case of a parallel plate system. You can see that the velocity of a particle is not uniform. So, velocity at the periphery is given by velocity of a particle at the periphery can be given by V is equal to WR. WR is nothing but the rate of rotation of a top plate. So, at the periphery V is given by WR, where WR is the rate of rotations of the top plate. So, the particles between the 2 plates is not subjected to a uniform motion. So, it will be maximum at the periphery and 0 at the center. So, by oscillating the top plate, we are subjecting the material to a sinusoidal shearing. So, you can control the speed and the deflection of an oscillation, so that we will get a controlled sinusoidal shear strain or controlled sinusoidal shear rate or controlled shear stress. So, we control the oscillation in such a way that the material is subjected to a sinusoidal strain or a sinusoidal shear rate or sinusoidal shear stress. Let us represent a shear strain by gamma and the rate by gamma dot and the shear stress by tau. So, now we give a sinusoidal shearing, because sinusoidal shearing is closely simulates the traffic conditions, loading and unloading conditions in the field. So, we generally use a sinusoidal shearing for testing a bitumen. So, it can be when you control a strain, we call it as a strain control test, or when you control a stress, we call it as a stress control test. We generally prefer strain control test for a bitumen. So, in a strain control test, we subject the sample to a sinusoidal strain and we find the response of a material. So, to subject the material to a sinusoidal strain, we have to give a 2 inputs. One is the speed at which you oscillate. So, if you control the speed at which you oscillate, that defines the frequency or a time for completing one oscillations. So, this time, this is inversely related to a frequency. Let us denote the frequency by omega. So, the time here, or time in seconds, is related to the frequency, and the maximum deformations you subject when you are oscillating the plate is defined by giving a strain amplitude. So, gamma naught here is a strain amplitude or a peak value, and omega here is defined as a frequency. This frequency can be related to the speed of a vehicle. When a vehicle is moving at a faster rate relatively, say for instance 80 km per hour and 40 km per hour, if you consider both these cases, when the vehicle is moving relatively at a faster rate 80 km per hour, the time at which the material is loaded will be less. So, less time or otherwise high frequency. Inverse of time is frequency. So, as otherwise it is a high frequency. In case 40 km per hour compared to 80 km per hour, its loading is more or more time. So, we need to test it at low frequency. So, if you want to simulate the response of to 40 km per hour, use the corresponding low frequency, and if you want to simulate the response of 80 km per hour traffic, you test it at high frequency. Now, what is the relation between the speed of a vehicle and the frequency of a test? So, now for to getting these relations, we will take a speed of 80 km per hour. 80 km per hour. So, converting into meter per second. So, 80 km per hour converting to meter per seconds, you will get roughly 22.2 meter per second. Let us find the time for the vehicle which is running at 80 km per hour, time of contact which it has with the pavement when the length of contact is say 2.2 meter. So, if the length is 2.2 meter and the speed is 22.2 meter per second, the time of contact will be maybe 2.2 divided by 22.2, which is will be approximately 0.1 seconds. So, this 0.1 second contact time, if you convert it, you will get 10 hertz frequency, which is nothing but inverse of time. So, 10 hertz frequency. So, if you want to test or simulate the response of a material for a corresponding to 80 km per hour, we need to test the sample at a frequency of 10 hertz. So, we control a frequency, we control a strain amplitude. By controlling a strain amplitude and a frequency, we subject the material to a controlled sinusoidal strain. So, our strain is an input here, we control the strain value. Now, what will be our response of the material if you subject the material to a sinusoidal strain? So, the response is measured in terms of torque or resistance of the material to flow, and this torque is converted to stress. Now, let us see what will be the stress response when the material exhibits a elastic behavior or purely viscous behavior, viscoelastic behavior, which is a combination of an elastic and a viscous behavior. So, we will see what will be the viscoelastic response for the sinusoidal strain. So, for an elastic behavior, when we subject the material to a sinusoidal strain, the red color one is a strain waveform. So, we have given an input for this strain amplitude, which we defined it as gamma naught strain amplitude, and it is a sinusoidal waveform. So, if we want to mathematically represent the strain sinusoidal waveform, we can write it as gamma to be gamma naught sin omega t. It is a sine waveform with the amplitude to be omega naught and the frequency as with an amplitude to be gamma naught and a frequency as omega. So, now if the material exhibits a elastic behavior, the response of a waveform will also be sinusoidal. The response waveform is a stress waveform here, the stress waveform will also be sinusoidal. The main thing which we have to understand here is the response stress waveform is sinusoidal, but with the same frequency. So, here you see the frequency of the waveform, the time taken to complete one waveform is same for both stress and strain. So, you can write the stress waveform for the elastic response to be a peak value of stress, we call it as a stress amplitude tau naught into sin omega t. So, the point you have to note here is the peak stress and the peak strain value occurs at the same instant of time. 0 stress and 0 strain value occurs at the same instant of time. So, there is no time lag between stress and strain when the material exhibits a elastic behavior. So, what will happen if the material is viscous? So, in case if the material is viscous or ideally Newtonian behavior, we subject the material to a sinusoidal strain, what will be the response of a material? So, we know that for a Newtonian material, stress is proportional to strain rate. For a controlled strain of gamma to be gamma naught sin omega t, strain rate can be obtained by differentiating this equation, partial differentiation of this equation. We can do that only if the response of the material is linear, that is very small deformation. So, gamma value, especially the peak value here is very small, so that the response is linear. So, gamma dot will, if you differentiate this expression, maybe expression A we call it as, if you differentiate this expression or do a partial derivative, you will get gamma naught omega cos omega t. So, gamma dot is a cos function. So, stress being proportional to a gamma dot, or you will get the stress will be equal to gamma naught omega into some constant, we can write it as tau naught. So, tau naught cos omega t. So, our control function is strain, which is a sine function, and the response function is a stress, which is a cos function. So, we know that the time lag between a sine function and cos function is pi by 2 or 90 degree, and we call this as a phase lag or phase angle. Phase angle for a pure viscous material is pi by 2 or 90 degree. So, since the phase lag is 90, which is nothing but the lag, peak value lag between stress and strain here. So, you see a stress peak to be at this location and strain peak to be at this location. The time lag is what we call it as a phase lag, and it is represented generally by delta. So, we will use a delta term here to represent a phase lag or a phase angle. So, this is ideal Newtonian material. So, we have a elastic material with a phase angle of 0 degree, no lag, and viscous material with a phase angle of 90 degree, maximum lag. Now, for a viscoelastic material, we can say that it exhibits a combination of an elastic and a viscous behavior. In such case, for a viscoelastic material, the phase angle delta will lie between 0 to 90 degree. So, we will keep this concept to frame the stress equation for a viscoelastic material. So, for a sinusoidal strain control test, if the material exhibits a viscoelastic behavior, we also get a sinusoidal stress with the same frequency, but the lag value here, that is a time lag between a peak stress and a peak strain, will lie between 0 and 90 degree. So, this is the basic concepts which we are going to use to define a material functions. So, let us write a equation for a strain and stress. So, we control a strain, and so strain can be written as gamma naught sin omega t sinusoidal strain, and the stress function is also sinusoidal. So, with a peak value, let us define a stress peak to be tau naught. This is also sinusoidal sin omega t, but there is a lag here. So, the lag is defined as delta, and we know that stress leads the strain value, that is, you need a minimum load to be subjected to induce a deformation in a material. So, we will get sin omega t plus delta. So, this is when the material exhibits a linear behavior and when the material exhibits a viscoelastic behavior. If we control a strain in a pattern of gamma naught sin omega t, you will get the stress response in the pattern of tau naught sin omega t plus delta. So, this is a stress response in a strain control test. Now, what about a stress control test? See, we are controlling a strain in a sine waveform. Now, if we control a stress in a sinusoidal pattern, what will be our strain response? So, let us plot the stress response of a stress control test. So, in a stress control test, let us assume or let us subject the material to a sinusoidal stress, because this is a stress control test. So, we will keep a sigma naught to be a amplitude of the material, amplitude of a waveform, and omega to be a frequency. So, we can write, we will represent it by tau, because it is a shearing. So, we will represent it by a tau. So, tau equal to, we are controlling a stress in a sinusoidal pattern with an amplitude tau naught. So, tau can be written as this expression. Now, if we have tau to be this, if the material is elastic, the response is going to remain the same, the strain response is going to remain as a same sine waveform with the amplitude of a strain to be gamma naught sin omega t, where delta is 0. This is in case if the material exhibits elastic behavior. For the material that exhibits a viscous behavior, the gamma is as we know, tau is proportional to gamma dot. So, the gamma is going to be a cos function. So, we can write it as gamma naught cos omega t. So, this is viscous. If it is a viscoelastic, the gamma function or a response function is going to be gamma naught sin omega t minus delta, stress leads strain. So, it is minus delta, this is viscoelastic. So, here this delta is 90 degree for viscous material and delta varies from 90, 0 when elastic to completely viscous 90. So, viscoelastic the delta value varies from 0 to 90 degree. So, now if you sketch the response function, let us sketch it on the same line. So, if you sketch the response function, strain response function, it will also be sinusoidal with the same frequency. So, if the frequency waveform is this is omega, this will also be omega, but there will be a lag, and this lag here is delta, and the stress waveform is given by this expression. This is in case if we conduct a stress control test. So, now just to quickly summarize, elastic material, if you subject the material to a strain control or a stress control test, it does not exhibit a phase lag, or phase angle for this material is 0, and for a viscous material the phase angle is 90, and for a viscoelastic material the phase angle varies between 90 to 0. See, 90 degree fluid, ideal fluid, 0 degree ideal elastic or a solid. So, you have a between value which is intermediate value 45 degree. So, what happens when the phase angle is above 45 degree or when the phase angle is below 45 degree, that let us discuss a few slides down. So, this will be an ideal stress strain plot for a different material, elastic, viscoelastic, elastic, viscous and viscoelastic material for a sinusoidal shearing. So, stress strain plot for a elastic material is straight line, for a viscous material is perfect circle as a phase angle is 90 degree, and for a viscoelastic material it is elliptical. We call this viscoelastic material stress strain plot under oscillatory shearing as a Lissajous plot. This Lissajous plot will be more useful when we are trying to find out the energy dissipation in a material. We know that the area enclosed in the stress strain plot is what we call it as energy dissipation, or we use a stress strain plot area in calculating energy dissipations. So, we know the response of a material to an oscillatory shearing. So, we can either do a stress control test or a strain control test. Now, what is the material functions? We use it for defining the material under oscillatory shearing.